Okay, let us now get some elementary understanding on the diffraction of light. Is the diffraction of light is the process of the bending of light or spreading out of light when it passes through an aperture or interacts with an obstacle. For example, suppose we have a slit of say size which we call B, and we shine this by a parallel beam. If this is opaque, this is opaque to this wavelength, then it will block the light, but the rest of the light will pass through the slit, the opening. However, this will be angular spread of an angle theta, which we call angle of diffraction. And this angle of diffraction can be shown to be ratio of lambda by d, where lambda is the wavelength of light and d is the, for a circular aperture, d would be the diameter. So basically d is the size of the opening, size of that. And if you have an obstacle and you shine it with that same light, then light of course will pass through when there is no obstacle, casting a clear image, sharp image, the obstacle, where light cannot enter. But light indeed enters, leaks into it because it bends here. This is the size of the aperture. So theta is there, right? Now you see, if d far exceeds lambda, and this is normally the situation that we encounter in our nature. Most of the obstacles, regular life, day-to-day life, their size is much, much more than the wavelength of the visible. So if this happens, then theta, as you can see, tends to 0. It is negligible. There is hardly any diffraction. That is why for normal objects that we encounter, the size is so much more compared to the light, that is visible light, which our eye wants. We don't see such effect like light getting into the shadow, geometrical shadow, because the obstacle size would be so much more than the wavelength of light that there would be hardly whatever bending it would be negligible. By naked eye, you cannot see. So the image will remain sharp. However, if d approaches lambda, then the angle of divergence becomes significant. So this is analogous to the situation. Suppose you are trying to walk through a gate. If the gate is very wide, then you pass through it almost oblivious to its presence because the gate is not wide. However, if the gate is very narrow, then you will have to maneuver, like you have to take a 90-degree turn and manage to squeeze through. It is exactly the situation here. If the aperture is much more than lambda, that is, the gate is wide, the light will pass through without any hindrance, without even knowing that aperture exists. However, if much smaller, approaches the wavelength, then the light spread. See, the you know the diffraction, principle of diffraction can be applied to tune a laser. So the principle of that actually comes from here. See, angle of diffraction depends on lambda. So suppose you have aperture and you shine light, so it's just two wavelengths, lambda 1, lambda, and they are not separable. They are all moving in the same direction. Now, when this, suppose this lambda and the aperture size, they're similar, so there will be diffraction. So the two wavelengths, if suppose lambda 2 is more than lambda 1, then the one with longer wavelength will also have higher angle of diffraction. So the two lights will be diffracted with different angles. This is lambda 2 and this is lambda 1. So the diffraction actually separates them. So once they're separate, then that actually allows you to maneuver them separately. So you will be able to tune it just by the same concept of prismatic, that you use prismatic dispersion to tune a laser. You may recall that you put, this is your gain medium, this is the back mirror, and suppose the laser can go on many wavelengths, so you put a prism here. All these wavelengths, which are not separable on this side of the prism, as they travel through the prism, they spatially split the different wavelengths. And so you put your output mirror in such a way that only one of these wavelengths falls normally. Others will fall obliquely, would simply get lost. This wavelength alone would be able to. So you actually choose the wavelength, and by tuning either the prism or this mirror, you can select different wavelengths. So you can tune the laser. Exactly similarly, you can do the tuning of a laser by making use of the principle of diffraction. Basically, what you use, say, I consider the case of opaque obstruct. You can arrange them in a periodic number of multiple such obstacles. And this is called grating. And this is actually a reflective grating, because if you shine light on it, the light will be reflected. This is called reflective grating. Now, if you shine light of two wavelengths, lambda 1 and lambda 2, so the two wavelengths will be diffracted in two different angles. So, in the actual operation, how do you use the grating? You have your active medium, then you have, of course, one mirror here. And you put the grating. Suppose you have number of them, say lambda 1, lambda 2, lambda 3. They will be refracted in different direction, different wavelengths, lambda 1, lambda 2, lambda 3. And you put your output mirror in such a way that at a time there will be only one of them will fall normal. So this alone will be able to reflect back and forth. The other wavelength components simply get lost, would not get a chance to provide feedback or oscillate back and forth inside the cavity. Either by tune, you can tune the grating, or you can even tune this, rotate this, angle tuning. You can choose different wavelengths. So this way, you can actually tune the wavelength of the. As a matter of fact, grating is very widely used as a tuning element for a variety of lasers. And in fact, the resolution power of grating far exceeds that of prism generally. Say, I can give you some example of diffraction. And this diffraction occurs not only for light wave, for any wave. Whenever wavelength approaches the dimension of the object, there will be diffraction. For example, you see, in your house, you can hear, say, your mother, maybe in the kitchen, and you are in the living room. You can see your mother, but you can hear her. Because the sound wavelength is much, much longer than typical visible light. So even common objects, furniture, door frame, window, they would refract the sound wave. So diffract means they will bend when they interact with an aperture, an object, it will bend. So they will undergo multiple bending. And from the kitchen, the sound wave will eventually find a way to reach your ear in the living room. But light wavelength being much shorter, they will not undergo diffraction in such obstacles, such objects. So they will rather travel in straight path and would not find a way to reach you. So you can hear someone while you cannot see that person. There is another example. I must also show you this. This is how the light enters shadow due to diffraction. I of course mentioned it. Now let us consider this one. This is light wave of wavelength lambda 1, and this is the obstacle whose dimension is A. And In this case, let us consider A is much more longer than, much bigger than, larger than lambda 1, the wavelength. So it will cast a sharp shadow because the diffraction will be almost negligible. However, if for the same aperture, now we increase the wavelength, so much so that the aperture and wavelength now tend to be of similar value. Then the light bends around the edges, reaching areas not possible otherwise. The diffracted light is shown here in a different color for easy identification. So this is the light which has leaked into the geometrical shadow, where this was a sharp, cast a sharp shadow. Here light actually leaks into the shadow as a result of diffraction. This is a glaring example of diffraction. The dazzling color which is thrown onto the sky when sunlight trickles through the cloud after sunrise or before sunset. The cloud, there is water particle. This has been possible as the white sunlight because you see the light when diffracts, different color diffracts at different angle. We just discussed, and this is what is actually exploited to tune a laser because this actually splits the different color spatially. Now, white light we know has 7 colors. So when they trickle through cloud, there are water droplets. The size of the water droplet can match that of the wavelength. So there will be appreciable diffraction. And different color will be diffracted in different angle. So the white light then will straight into this majestic pattern of color. So I think I stop here now and we'll begin from the next class from the scattering of